Hi everyone, I'm Stephanie, and today I'll be talking about the Lineage stash, which is a system and technique for recovery in low latency data processing systems. So low latency today is becoming increasingly important in data processing, and that's because data processing is being deployed more and more in online systems. We're seeing it being used to power decisions that affect the outside world in application domains ranging from stream processing to graph processing to control systems. Because data processing is computationally expensive, it's also necessary to scale out these systems to multiple nodes. And because of that, a second requirement is the ability to recover results after a failure. And if you combine that with the low latency requirement, it's also desirable to recover results as quickly as possible. But unfortunately, there seems to be a hard trade-off between low latency and recovery time. And that's the problem that we'll be addressing today in the Lineage stash work, which aims to achieve both low runtime as well as low recovery overhead. And to show why recovery is so hard in systems today, we'll work with an example in stream processing. In stream processing, the user gets the abstraction of executing some function over an infinite stream of records. So in our example, we'll work with a search query application, and we want to build a dashboard that displays the number of times the word UCB has been queried. So the input records in this case will be dictionaries that represent a user query, and we'll push it through several operators that first select the keyword from the query, then filter it based on whether it's equal to UCB or not. If it is, we can send it to a counter operator that has some internal state, which will increment every time we see the word UCB. And finally, we can write the results to an external database where they can be displayed in a dashboard. So this is just one example in stream processing, but in general, we expect the end-to-end latency of such a pipeline to take in the tens of milliseconds. And we'll see next how we can execute a system to do this. So in our system, we'll instantiate one process for each of these operators, and we'll show the messages that are sent between the processes over time. So we'll begin by sending an input record to the select operator. And although the abstraction in stream processing is record at a time execution, we'll actually want to execute over multiple records at once so that we can batch them together for efficiency. So to process this batch, we'll launch a message handler, or a task, which is a unit of computation that takes in some input data and that can also produce some output data. So one thing to note here is that because the end-to-end latency is so low, the tasks here are also very short. So they may take only a few to tens of milliseconds. And here, tasks can also create more tasks. So we might create another task on the filter operator that includes the extracted keywords. To scale out a system like this, we can create multiple instances of the operators. So here we can create two select operators that can now execute tasks on different batches of the input stream in parallel. So we can continue running this application, and now maybe we'll send a +2 task to the counter. So next, let's walk through how systems today achieve recovery for stream processing systems. So first, we'll look at a global checkpointing technique, which is one of the two main recovery techniques. In this approach, we'll take a consistent global checkpoint across all of the operators on some time interval, and we can do this asynchronously to reduce the runtime overhead. And now if we continue running through this application, we can see what happens when there's a failure. So let's suppose that before we're able to send this last +1 task to the counter, the filter operator fails. Now in this case, we want to make sure that all of the input records are accounted for in the counter's final state. And so we'll have to roll back a process here and replay some of the lost tasks on the filter operator. So here we can maybe start by rolling back just the filter operator. But in order to do this, now we'll also have to roll back all of the upstream processes so that we can reconstruct the intermediate messages that were sent from the select operators to the filter operator. This brings us to a second issue, which is that the filter operator actually executes tasks in a non-deterministic order because it receives tasks from multiple operators. So here, we might actually execute this third task first this time. And so now, this is an issue because it's inconsistent with the counter state. The counter had some internal state which depended on the initial order of execution, and now there's an inconsistency here. So in order to handle this case, we also have to roll back all the processes that are downstream to the failed process. And once we do that, now we can run the application forward again and get a correct result. So in summary, for global checkpointing, the runtime overhead is usually very low because you only have to spend time doing this global checkpoint during execution. But the recovery overhead is much higher because you have to roll back the entire application upon any failure. And as these systems scale out to larger clusters, the recovery overhead becomes even worse because the chance of a single node failure increases. So this is in contrast to the second approach that I'll talk about, which is logging. So in this approach, the goal is to record additional information during execution so that you only have to replay the work that was failed. So we can minimize the amount of computation that needs to be redone. So in this logging approach, let's see how we can do that for the filter operator. So here, to make sure that we can recover it, we'll have to record two things. First, the messages that are sent from the select operators, and then the order of execution on the filter process. And that's because this was a non-deterministic decision. One thing to note is that in logging, we actually still take global checkpoints, but this time it's just to bound the recovery time and so that we can eventually garbage collect the logs. So next, if we walk through the same failure scenario here, where the filter process fails, now we'll still have to roll back the filter process, but this time we can just use the logged information to replay only the tasks on this process. And once we do that, we can see how we can actually get the correct result at the end, where all of the input records are accounted for exactly once. So in a logging approach, the idea is to record additional information between checkpoints so that only the failed processes need to be rolled back and replayed. And that reduces the recovery overhead, but the runtime overhead is much higher than in global checkpointing, and that's because you have to record this additional information during runtime. So one approach to reduce the total amount that has to be logged is to only log the lineage instead of the data itself. And what I mean by this is to basically take the messages that are sent between processes and to just cache that in memory. And then the thing that we actually store persistently is just the pointers to that data. Now, if that data is lost, we can also persistently log the descriptions of the tasks that created that data, and we can replay that in case of a failure. And this is what I mean by the lineage. It's these task descriptions. So while this reduces the total amount of data that we have to log, unfortunately, logging can still be expensive in low latency data processing systems. And that's because it still requires a synchronous round trip on the critical path of execution. And basically, this is because we have to actually make sure that the lineage will survive across any process failures. So we can see that here, where if we want to send a task from the select one operator to the filter operator, we have to first write it persistently to the global lineage store, which must be on a remote node, and then wait for the acknowledgement before we can send it to the filter operator to be executed. So this means that besides the minimum RPC that we need to forward the task to its destination process, we also need to spend at least one round trip to make sure that the lineage survives on a different node. So optimistically, this round trip time might only be 1 millisecond, but even that can be a lot when the tasks are only a few milliseconds long, and if we have to do this before every single task. So really, the problem here is that the task latency depends on the global storage latency. So in the worst case, the global store might actually become the bottleneck for certain applications. So this brings us to the contribution of the lineage stash work. And the question that we're trying to answer here is how we can achieve both low runtime and low overhead in recovery for fine-grained data processing applications, where the tasks run on the order of milliseconds. And the solution is basically to log the lineage, but to do it asynchronously, so that the runtime cost is off the critical path of execution. And this combines two key ideas. One of them is lineage reconstruction, which allows us to reduce the total amount logged by not logging the data, and causal logging, which is a technique for asynchronously logging non-deterministic events. So first, let's walk through the lineage stash architecture. So this is a decentralized architecture that looks very similar actually to the synchronous logging approach. So we'll have the global lineage store, which is really just a persistent key value store. And we can shard this for horizontal scalability, and then replicate it also for durability. Each of the processes will also have some local volatile state. So we'll have one local volatile object store, which can be used to store application data. And we'll also have a volatile cache for the lineage, and this is known as the lineage stash. And we can see next how we can use this local stash in order to log the lineage asynchronously. So if we look at the same example before, where we want to forward a task to the filter operator, instead of writing it synchronously to the global storage, we just have to write it synchronously to the local lineage stash. And this can happen almost instantaneously. Next, we can flush it to the remote storage, but at the same time, we can actually forward the task immediately to the destination process to be executed. And that reduces the scheduling delay for each task to the minimum of 1 RPC needed to forward the task in the first place. So you might be wondering here, now that we're logging it asynchronously, what would happen if we actually lost a lineage stash before we were able to persist it to the global lineage store in time? And we'll go through that next. And basically, the idea is to use a causal logging approach where we piggyback additional information on this task forwarding message. So in this example, we'll just look at 2 of the processes, and here we'll have a filter process that executes 2 tasks in a non-deterministic order. So it'll do that by first adding the task to its stash, and then flushing it to the global lineage store. And it has to do this so that we can record the non-deterministic order as part of the lineage. Now let's suppose that the second task here creates a task for the counter, and in order to forward this to the counter, we'll first have to add it to our local stash before we can forward it over to the counter to be executed. So one thing to note here is that this last task actually depends on some part of the lineage that's been uncommitted. And that's because this non-deterministic order of execution hasn't been persisted yet in the global lineage store. So in order to guarantee that we can actually recover correctly in case of a failure, we'll actually have to forward this information along with the task to the counter's lineage stash. And we'll see why we have to do this in a second if we look at a recovery example. So now, let's suppose that at this point, the filter operator fails. And that means that also all of the in-flight operations would have failed here. So now the issue is that the counter has some internal state that actually depended on this initial order of execution. But now the counter process is the only one that has that information in its local stash. So in order to recover, we can actually use the global lineage store as an intermediary between the 2 processes. So the counter process will first flush its local lineage stash to the global lineage store, and then acknowledge that to the recovering process. Now that the lineage is in the global store, the recovering process can just retrieve and replay its lineage from the global lineage store, and this step is actually exactly the same as an asynchronous logging approach. And so that's what allows us to get the low recovery overhead in addition to the low runtime overhead. So next we'll look at some results from a stream processing application. So looking first at the runtime overhead when there are no failures. So we'll use a simple streaming word count example on 32 nodes. And as a baseline, we'll use a global checkpointing alone approach on the system Flink. We'll compare this first to an approach that we call write first, which logs the lineage to a global store on the critical path of execution. And you can see here that it's actually not even able to keep up with the target throughput here, and that's because of this additional latency on the critical path. Next, if we look at the lineage stash, which actually logs to the same global store, but in this case it does it asynchronously, and so it's able to get latency that's comparable to Flink's. So next we'll look at the performance during recovery. So here we'll start by running all of the systems until we take the first global checkpoint at time 30 seconds. And then we'll introduce a node failure at time 45 seconds. So at this point, Flink will have to roll back its entire system and then play it forward again to redo the lost work. So during this period, the throughput will drop to 0. And so it has to replay the last 15 seconds amount of work. Next, it's able to process all of the new records that entered the system since the failure occurred. And because we over-provisioned the system, it can use that additional capacity to catch up with the input stream. And if we compare this to the logging approach, you can see that the 2 logging approaches, in both cases, the throughput drops only slightly, and that's because you only had to roll back the processes that failed. And we can see also how this impacts application level latency. So looking next at the same experiment setup, but this time measuring the latency for each of the records in the input stream. And you can see that after the failure, the application level latency for Flink jumps dramatically, and that's because these new records were blocked by the global rollback. Meanwhile, for the two logging approaches, the median latency actually stays about the same as during normal execution. So although at the failed processes, the new records were actually blocked by the recovery process, the remaining processes were actually able to continue processing new records safely. So today I presented the Lineage stash. I only had time to go through a few of the details, but you can see the paper for some more details on other applications, on how to handle non-determinism and data processing, and also the full protocols for flushing and recovering the stash. The key idea in the Lineage stash is to asynchronously log the lineage, and then to forward any uncommitted information to guarantee recovery correctness. And that's what enables us to get low latency during execution, as well as low downtime after a failure for large-scale and decentralized data processing applications. Thank you.
Hey, so I'm Chinmay from Utah. I had a question about your recovery protocol. Do you mind going back to the slide where you actually showed the case where one of those nodes crashed?
Here?
Yeah, here. So I was wondering if your recovery process, so what if you were to recover the node that crashed before the other node actually conveyed all the information back to the node that...
Oh, yeah, so I guess I wasn't clear about this in the presentation, but this step actually has to happen synchronously. So in the next step where you acknowledge, you have to wait for the global store to acknowledge all of the rights.
So then how does this scale with the number of nodes in your cluster? Are you assuming that there's only one, are you assuming that there's going to be only one arrow coming out from one of those yellow circles? Can it be like broadcast or something like that? Wouldn't it like scale poorly if the fan out were pretty high in that case?
Yeah, so there are two things you can do. One of them is just to only contact the processes that the failed process was actually talking to initially.
Okay.
But the other one is also that like all of this can happen in parallel. So all of the nodes can actually write to the global store in parallel.
Okay.
And the global store itself is also sharded. So it looks here like it's a centralized system, but it can actually be
So you can use all nodes in your global store to kind of like recover.
Yeah.
Okay. Thank you.
This is Hong from Cornell. It's a very good talk. I have a question about the throughput, because most of the evaluations are about latency. It seems the filter sends more messages to the counter. How does that affect the throughput?
Sorry, the question was about if the filter
the filter sends more messages to the counter than the logging approach. Mm-hmm. How does that affect throughput?
Oh, I see. So yeah, so I'll compare this first to a synchronous logging approach. So in synchronous logging, your throughput is bottlenecked by the throughput of the global store. Is that what you're talking about? And then for like this approach where you're asynchronously logging, in the end, like you still will be limited by the throughput of the global store, but you do actually get a little bit of buffer here because you can sort of like temporarily buffer things in your local stash. And you can also scale up the global lineage store. So you can scale it out to, you can shard it for scalability.
Oh, I see. Thank you.
So Ethan Miller, UC Santa Cruz. I actually had the same question. I'll try to clarify it. It looks like you send the message from the filter to the global lineage store, and if you then contact the counter, you send the uncommitted message. So isn't that sending the same message twice? In other words, isn't the bandwidth going to be higher because you're sending the same message twice, once to the global lineage and once to the counter?
So I mean, the bandwidth there I think should be different because it's not, the counter isn't on the same node as the global lineage store.
Right. And that means you're sending the same message 2 times as opposed to logging where you get a response back and only send it once.
Right, but you would be sending it to a different node. So the bandwidth is not, like the bandwidth that you need to consider is not just between the nodes and the global store, it's also between the processes. And so I think in this case, like the total throughput of the global lineage store is still or the total load that you're putting on the global Lineage store should be about the same.
Okay, we'll talk offline about it. Thanks.
Okay, yeah. Thanks.
Let's thank the speaker again.